See, look.
And at the end, there's a bunch of little emoji things that you can put up in there and copy and paste.
I was worried when I got the clicker it wasn't going to work for this, and I did it.
Oh, yeah. I love the clickers. She's ready. Clickers, my new best friend. All right. Isotopes.
Yes. Okay. So, hello everyone. How's everyone's night going? Good.
I want a donut.
You want a donut?
A freaking jelly donut.
Oh, Bailey.
That in my notes, by the way.
Okay, so today we're going to be talking about isotopes. Okay, so what do you think is, like, why do you think I put this picture of these two cute little babies or these cars that have very, what are you thinking?
Is it something that's similar but different?
Exactly. Does someone want to build upon that? Something that's similar but different?
Kind of like, I guess, in the way that they're twins, but they may inside or maybe their weight could be different.
Oh, their weight. Excellent.
With the cars, the same thing, but different models.
Exactly, right? So this maybe is like the basic car with upholstery, which is like standard, right? Standard. And then this one maybe has like the leather seat. And then maybe this one has like the backup camera and all that, right? Okay, so something's a little bit different. Okay, and that's exactly, I'm glad y'all saw that because we're going to talk about isotopes. And isotopes are atoms. They are atoms, and as we know, atoms are the building blocks of matter. Atoms are the building blocks of matter, right? Okay, so because we know that atoms are the building blocks of matter, isotopes are atoms. They are just alternative versions of these atoms, okay? So just like these little twins, this could be, maybe this twin weighs 20 pounds and this twin weighs 19 pounds. They're the same, they are identical, but this one just weighs a little bit more. So alternative version, and that's what we're going to go into. Okay, so this is a quote that I'm reading Michelle Obama's book right now, and it's really good. I would recommend it. It says, "Do we settle for the world as it is, or do we work for the world as it should be?" So usually we would have a little discussion, but time. Okay, so our agenda. We are going to do a little review. I know we're all really comfortable with atoms, but we're gonna still kind of review that a little bit. We're gonna go into our structure, my lesson, which is isotopes, have an activity, and we're going to check for understanding. And y'all should be able to define isotopes, determine isotopes mass number, and all of this fun stuff. Yes. All right. Okay. So why do we need isotopes? Okay, Merlin, would you mind reading the first line, or the first little paragraph?
In 1991, in the Alps, near the border between Italy and Austria, two hikers found a preserved body in a melting glacier, the oldest known natural mummy in Europe. The corpse sparked curiosity throughout the scientific community. He was nicknamed Atatsi, the Iceman, and everyone wanted to know what kind of life he lived 5,000 years ago.
Okay, and then Bailey, could you finish the last?
Using isotope science, scientists were able to draw conclusions about where Otzi might have lived, both as a child and as an adult. This kind of forensic work is not the only use for isotopes. From the food we eat to catching athletes that cheat or understanding planets in space, isotope science has a vast array of applications.
Perfect. Okay, so isotopes can be used for, question.
Did I just say catch athletes cheating?
Yeah.
Cheating on what?
Cheating, like if they have, what is it called? Like doping, when you are.
So see if they're actually doing drugs. I thought you meant like cheating during a game. I was like, isotopes during a game?
Why, what?
I thought you meant that they were using isotopes during like
no,
games.
it's
So
just
when
they have to pee or when they take their blood
so now
samples.
it makes sense.
Yeah, exactly.
So you find out they're actually cheating.
Exactly. Yeah? Okay. So isotopes can be used for, we just talked about it, like the cheating scandals, I don't know. But you can use it, you see it happening, radioactive isotopes in agriculture, food industry, pest control, archaeology, and medicine. And then, Mario, can you read the second one?
The radiocarbon.
Yeah, carbon.
Radiocarbon dating, which measures the age of carbon-bearing items, uses a radioactive isotope known as carbon-14.
Perfect. And then, Bailey, would you mind reading the last one?
In medicine, gamma rays emitted by radioactive elements are used to detect tumors inside the human body.
Okay, so that's really awesome. There's all these ways that we can use isotopes, and the way that medicine and a lot of really smart scientists are using it to prevent cancer. So that's really awesome, or prevent the growth of cancer and more. So there's really really good uses of isotopes. All right. So the word isotopes comes from the Greek iso for the first part, and then iso means equal, and topos, which means place. And they're called this because they have different atomic weights, like y'all said. They weigh differently, but they look exactly the same. They're actually gonna react the same way. The only difference would be a little bit of physical difference, but you wouldn't even notice it. Okay? So they're different versions of an element, different versions of the same atom. How do we feel? Feel good? Okay. And there's ways that it's written. It's called an isotope notation. And basically you're going to have this number up here is your mass number. This number down here is your atomic number. And then your symbol, this X, is the actual symbol of the element. Most of the time you won't see the atomic number. You will just see the mass number. So you see like this. But you will sometimes see it. And then an alternative way to write, this is saying the chemical name and then saying how many, the mass number, which is the protons plus neutrons. Okay. How do we feel? Good? Okay. Because we are about to do a little bit, I hope y'all feel comfortable. Because you're about to do it on your own. Okay, so I know we're talking about atoms. Everyone knows what is an atom, or what are the three components of an atom?
Proton, neutron, electron.
Perfect. Protons, neutrons, electrons. Where are the protons? Where are the neutrons? Where are electrons?
Protons, neutrons inside, electrons on the outside.
Perfect, right? So the neutrons, the protons are in the center of the atom. So this is an atom. Atom. We have the electrons on the outside and the nucleus with the neutrons and the protons. How do we feel? Good? Okay. Perfect. Okay, so our mass number is really, we talked about weight and how the isotopes weigh a little bit differently, right? So that's going to come into play when we talk about mass number. Because the isotopes weigh something different, that weight comes from the neutrons, okay? The weight comes from the neutrons. Our protons are always, always, always going to be the same, okay? Our protons never change unless we're talking about a completely different element, different atom. But if we're talking about oxygen, we're going to be talking about oxygen. Here's an example. They say neon 20, and they show you 20 as the mass number, because the mass number is on the top, and then 10 on the bottom, which is our atomic number. And this is neon 22. Where it shows you 22 as the mass number and 10 as the atomic. The atomic number did not change. The only thing that changed was the mass number. Good? Okay. So now, if y'all can please get out a piece of paper, draw a circle, kind of like this. Your circle's going to be blank in the middle. Just a circle with just a circle. All you need is a big circle. A big circle. Oh, you know what? I'm sorry. Wait, Bailey, would you mind coming to this center? Okay. And sorry about this one, that's all mixed up. But I know, okay? I know.
Almost someone listening.
I know, okay?
We were told someone was in sort mode.
So I want y'all to work together, and you can I want you to work with hydrogen. So maybe take one of each. So hydrogen 1, hydrogen 2, hydrogen 3. And then go to carbon, oxygen, and boron. Boron, yeah. And then our protons are black, and our neutrons are purple. Okay. And there's some keys up there to help us if we don't remember that mass number is actually the number of protons plus neutrons. And then our neutrons, another way to rewrite this is if you're looking for it, neutrons equals your mass number minus your atomic. So I can write it.
Can we have periodic?
Oh my gosh, I'm like, thank you, Bailey, yes. Everybody, you're always supposed to bring your periodic table, so Bailey.
She left her binder.
Oh my gosh.
I have some last period class.
Okay. I have some thank you, Bailey.
Thank you.
Some periodic tables. Because you literally cannot do this.
I mean, you can
We all have it memorized.
Yeah.
I'm sorry, you said you have it memorized?
Yeah.
Okay.
Just kidding. We don't.
Yeah,
We
and,
grew up back in the day where we had to memorize it.
We don't
so
learn
you want us to
didactic
calculate,
What?
sorry.
So we
I
don't
want to
learn
see your
didactic.
model of hydrogen one. Or you have to decide that as a group. Like, I'm going to take hydrogen one, I'm going to take hydrogen two.
Oh.
Well, Marlon already did
I
one.
did
So can I see what one looks like?
Yeah.
I'll do 3.
So I just do. I just wrote the equation up on top, and then just put the one each. So we got one for the mass number, and then got one for the proton, because the number right above it, and then we're trying to solve for N.
And then also, would you mind giving me actually a model of it as well? So on the side of your work, can you draw another circle
Oh,
and
yeah, yeah.
show me
Oh, and draw how it's
protons
supposed to look like.
and neutrons, which we're going to say our neutrons are going to be, blank space. They're neutral.
So the
Or you
first one
put it
should
in.
have 0 neutrons.
Sorry, you did H2.
I did 3.
So you
So
got
I love
H2.
H2. Okay.
Are we able to start on the next one?
Yeah.
I'll get 11 to 12.
Okay.
Or I'll do 11 14. Or even better, we'll just take the whole row.
Let's make sure our whole group is,
Want to do it that way?
So,
Right.
one quick second. So
Yeah.
the H2, right? The
Uh-huh.
one on that top. So that,
No, because there's 2 on top of that. So the mass number.
That's
Oh, yeah.
yes.
so it's,
So remember, whatever number's there, that's your mass.
So you're going to do 2 equals and then 1 because the atomic number is 1 and then plus n.
No, the proton's one.
I'm sorry.
and that's
Yeah.
mass number.
So mass number is the number in
So
front
it'll
of the
just
letter.
be 1, right? So is that how it works?
Yeah, but we're solving. I would write n,
And instead
so you know
of
what
1,
you're actually solving for.
Oh, okay.
Because that's what we're solving for is n. And then right below it, or next to it, you can write
Just
n.
kind of,
subtract the, yeah. And you get.
and then how would you actually put those inside?
So you would do, it'll only have 1.
Oh, I need a calculator.
It'll have 1 proton because that's the atomic number. So you'll do 1 black one,
Yeah.
and then that's your neutron, so you'll do 1 purple one. Yeah. And then you just draw, like,
But you put 3 because you had,
I took the 3rd, yeah. Okay. So I will do.
So you got the third row, and then you got the whole second row.
Okay, I'll take
the C's?
13.
Yeah, all of them. So the whole row, you got H2, C12, O17, and E11.
oh, good call.
Yeah, and then you want to do C14.
Yeah.
so you all can use beads, you can use, your own models.
big reserve
For what?
for these ones.
Why do you find that bigger?
Because the pluses, minuses, there's not enough for them.
Oh, okay.
So I just realized
Wait, why do you have minuses though?
for neutrons, huh? Is a neutron?
Remember the charges on the neutron?
Oh, electrons. Really? Guess I don't
It's just
remember.
null and
So protons are P plus.
Uh-huh.
The neutrons are just N's.
You're gonna say that what?
N's?
Yeah, you can say N's. And then, I don't know if you can see if it's hard to see, but yeah, for my first model, I have the positives,
Oh, there.
positive, and I just have infinity, and then on the top I have them with the N. So whichever way.
It was just for this one, it's 5 protons, 6 neutrons. So I just, I was like, oh, that's kind of small. But that's
And then we know that they would be like in the center, right? They wouldn't be like
just like
separate.
connected.
Yeah, but it's like, yeah, they would be together in the center.
Thank you.
You're welcome.
we're good.
Thank you, Mary. Okay, so. Okay, sorry. I was going to say that. Okay, so. Did y'all help each other? How do you feel about what we just did? Do you feel like you have a good understanding of it, Mario?
Yeah, I guess I was having a little trouble
Is it the
trying to figure out. Oh no, but when they helped me out, figure it out.
Mm-hmm.
I was
Okay.
thinking a little bit too hard.
Oh, okay, so then you'll be ready for this. Yeah?
A quiz.
You know, right?
Not a quiz, just a, you know.
I don't approve.
Huh?
So I was just kidding. That would be. You can remember it's asking for the same instance of what you're saying. And then what's the difference? The neutrons can be with 7 plus 8. You got it, right?
Yeah.
Okay.
I was just doing it.
Okay, just a quick backtrack.
Just so you know, I was very clear on that. Like, why do you have a bunch of letters with little numbers next to them? I don't see that. I have no idea what that's for.
Oh no.
You can what?
She's a tutor.
Just a quick backtrack. How did y'all figure out how I want you to explain it. Maybe Mario, how did you figure out how many neutrons for, what did you have? Option 17?
17. So the first thing I did was I took 17 minus 8, and the reason I put 8 because oxygen has 8 for its atomic number.
Perfect.
So I subtracted 8. Negative. I subtracted 8 to 17. I got 9. So I got 9 neutrons.
You got 9 neutrons.
Mhm.
Okay, which changed its mass number because. Okay. No, I'm just gonna leave it at that. Okay. What about you, Bailey? How did you have C13? Or,
Yeah.
How did you figure out C13?
So I took 13. I did like one. So I did 13 equals, and then I took 6 because that's the number of protons in carbon plus n, and then I subtracted 6 from each side and got n equals 7.
Perfect. Is there anyone who did a little bit different, or did we all kind of follow the same thing of like neutrons equals protons? Or minus all?
Well, I had just one thing. It I guess it was weird because you can subtract 6 from both sides, but then it's like after you figure it all out, you're like 6 plus 6 is 12. It's almost like you could have just skipped a step, but I don't know. I guess it could get more difficult as it goes on.
Bigger number.
So you're saying like
Kind of like just saw like 6 and 6 is 12, just like that.
Instead of actually
So
sitting
just
down
kinda
for
like-
just like see and click it in.
yeah. So I think we're gonna get to that level where we're gonna be like, oh, I already know this. I already have the formula in my head. I can just answer it. But right now we're just learning. So exactly. Okay. So what do we get? Oops, no. What do we get for could you Merlin? Which isotope below has 8 neutrons? Okay, why does it have? How do you know it has 8?
Because the protons on that one is 6, so we did 14 minus 6, which equals it.
Mm-hmm. So 6 plus 8 is 14.
Yeah,
Perfect.
the other ones didn't come out to 8 when we subtracted by their protons.
Perfect. Okay, so then what about you, Bailey? What about 2 isotopes?
It's their mass number C because the little numbers on the left of them is their mass number, and I couldn't have any of the other. I mean, they could have different numbers of electrons, but yeah.
That's true. They
Yeah.
could. Mm-hmm. I'm glad you saw that. Okay. Mario, last one. Which of the following have the same number of protons but a different number of neutrons?
Well, it's C just because they're both, is it lithium?
Mm-hmm.
And all the others are different, so they're all going to have a different atomic number,
Perfect.
which is different protons.
Perfect. So if we change the number of protons, we're talking about a completely different atom. So that's how we know. Like these two aren't even the same. So they're obviously not going to have the same amount of protons. Unless you start doing some radioactive stuff, which we're not talking about just yet. So, but yeah, the answer is C. Okay. And that's it. That's all I have to do.
Yeah, that is one thing with Slides Carnival. It has the entire presentation. So you have to go in and you have to like delete the bottom ones. So they're always like, oh, I don't really know what that one is. Oh, that's not my new one. Okay, I got it.
Last but not the least.
See, math at 9 o'clock at night.
Thank you.
You're welcome.
Thank you.
I've never felt better at chemistry.
Oh.
After doing it,
So much
she did that lesson.
Yeah, you should, like I said, you should try to repeat as often as you can. Because
And-
by the third time you do it, it's going to be way better.
Yes, and you did like so much.
Oh, thank
better.
you.
I feel bad for my first period class because, man, by fifth period, I got it down pat. Or first period, I'm like, I have no idea what I just said. When you teach the same thing 4 times, 5 times a day, you get better every time.